segment within this business unit. And transportation and mobility segment, we also support mobile robotics, in particular for logistics, for warehouse and factory automation applications. So today we're going to be covering an agenda. This includes briefly an overview of the NXP processing technologies or processing solutions, so that you have some context for some of the products that we're going to be using. Then we will be covering briefly, some of the actual market trends and challenges for mobile robotics, as well as autonomy for indoor robots. And then we will cover the actual architecture of the mobile robotics platform from NXP. And then we will show the internal vehicle connectivity and the different modules that are actually part of the platform that implement the different functions, like vehicle control and companion computer with the NavView Plus for doing some of the mapping and autonomous applications. And then we will go into more details on some of these modules, their key features, and review the functions they perform, the key capabilities they have, as well as the software enablement for these modules. Okay. So let's get into the actual processing continuum from NXP. So NXP has a scalable, processing solutions all the way from our very low-end flash-based microcontrollers. This includes the LPC, Kinetis, MCX, and S32K families. These can be used in a range of different sensors and actuators, vehicle management. This also includes with the automotive microcontrollers, ASIL D level safety capabilities. And then we have our crossover processor family. These are basically microcontrollers, but able to support kind of the application performance of low end of the application processors, but still have a microcontroller architecture and use a real-time operating system, so you still have the simplicity of design and deployment in terms of the design complexity of these solutions. And in the crossover family, we offer, and as well as in the MCU families, we offer a range of different features. In the in the crossover family, we have devices that also include integrated gigabit Ethernet switches. These switches can also support multi-protocol Ethernet, so things like industrial protocols, EtherCAT, Ethernet IP, Profinet, all kinds of different protocols can be supported by these devices. And those same protocols can actually also be supported on the lower end MCU, the MCX, Kinetis, LPC type devices as well. In terms of the application processors, we have a range of different solutions that are available. We have our ADRMX family, which includes a scalable portfolio of solutions all the way from single core to many cores. We have AI and machine learning hardware acceleration. We also have in the ADRMX family vision processing capability for machine vision, complete camera interfaces supporting multiple cameras, integrated image signal processors, video encode decode. Those types of capabilities are supported. Then with the S32G family, again, you have compute scalability, to many cores, as well as networking, hardware acceleration for packet processing capabilities. And also the S32G family supports many of the automotive interfaces and safety at the level of ASIL D with lockstep capabilities on the actual application cores. So if you need safety applications and, at the application layer, and S32G can provide you with those solutions. Layerscape is kind of our high-end processing solutions. This, again, has a scalable range of different devices from single core to 16 cores. And some of these also have integrated switching capabilities and TSN support as well, and a rich set of Ethernet interfaces, PCIe, and packet acceleration technologies as well, to kind of offload the software processing from the cores to more of a packet acceleration architecture, so you can have more headroom available for applications on the actual CPU cores. So let's get into the market trends and challenges. So just to give some context, historically, warehouses have used automated guided vehicles. These followed QR codes that were actually on the floor and magnetic stripes to follow a fixed path or a fixed route in a warehouse. And this was the norm. And in terms of recent, last few years, as the deployment has become complex. You need to install all these different magnetic stripes in order to make efficient use of these vehicles. And also processing capability has increased. So autonomy has started to get added to these mobile robots. So as you basically add autonomy, these vehicles are basically known as autonomous mobile robots. And now they don't need this infrastructure. They can actually map the environment. They can actually determine, how to get from point A to point B autonomously. So there's no need to install an infrastructure. So it simplifies the deployment of mobile robots in a logistics environment. So you don't have to install this infrastructure. You can almost pretty much from day one, once you download the maps to the mobile robot, you can be operational and ready to go to start performing, the different functions that are needed in a warehouse. There are also companies that specialize in the industry, and they basically provide, if you like, autonomy solutions. This can include software, which might be algorithms that make efficient use of the processing capabilities within the robots to make use of the sensors that are already there and give you the ability to, map and navigate the environment. There's also, companies that offer both hardware and software solution. So if you have an AGV today and you want to be able to turn this into an autonomous mobile robot, you could work with one of these vendors and they can give you the hardware and software to upgrade this to kind of autonomous operation. AI machine learning, this has already really become a key requirement for many automation applications and for warehouse operations in particular. And mobile robots are already implementing AI machine learning. This is needed to kind of avoid objects, to recognize objects, and also, to segment the scenes and be able to determine what, objects they need to avoid, what they need to pick up in terms of scanning, identifying objects, in the form of labels and, barcodes, etc. So this is all based on vision applications and also AI machine learning to constantly kind of enhance the images and also to accelerate that processing capability. Some of the challenges associated with mobile robots. So, first of all, number one is safety. In a warehouse operation, typically you're operating around humans. And in order to guarantee the safety of those humans, you have to implement some sort of safety functions. So if they come within a certain range of a person, they slow down. If they get even closer, they need to, slow down further or potentially stop. They may even also have emergency stops on the robots, just in case there's some kind of an emergency and you need to immediately stop these robots from performing some kind of a function. So those kind of safety features need to be implemented in these mobile robots. There's also sustainability. So, has become a key requirement and an important factor in warehouse automation. And this is really around helping to reduce the overall energy consumption within a warehouse. And automation can help with that. And one of the capabilities that actually helps with that is the ability to manage, peaks and drops in the actual workload for a warehouse. So it's a lot easier to do that with the mobile robots and automation than, dynamically determining how many people you need for a particular, task and then being able to manage that, plus being able to address labor shortages. This is, one way to basically do that. Okay. In terms of autonomy, for industrial robot applications to implement autonomy, you need, first of all, to be able to perceive the environment. So you need some way to see that environment, and that requires a range of different sensors. You also need to be able to understand the situation. So you need to be able to make sense of those scenes and identify objects and segment and recognize those objects. And then you need to be able to do locationing and determine your position within that environment so that you can actually now navigate from where you are to the destination that you need to go to perform the task that you have been programmed to carry out. In terms of the actual the navigation itself, there are algorithms that are used. SLAM, VSLAM, simultaneous localization and mapping algorithms are what's used for this path planning and navigation, along with AI machine learning to, as I mentioned before, to detect, recognize, and avoid objects. And you need sensor fusion. One sensor is potentially not going to be enough. If you just have vision sensors, if you have some kind of a glass wall, the camera is going to see right through that. It might not recognize that there's actually a wall there. So you need other sensors to be able to detect that there is actually a glass wall, something like radar or LiDAR. So you need to have a combination of sensors and do sensor fusion to be able to make sense of the environment and to be able to safely navigate within the environment. You also need reliable and low latency communications to integrate these mobile robots and warehouse operations into an Industry 4.0 infrastructure. So let's discuss the actual system block diagram for the mobile robotics platform. So this is the architecture that NXP has implemented. As you can see, this is a modular architecture, and we have multiple, different modules here performing different functions. And the modular architecture allows us to actually scale the capabilities of the robot over time. So if you need to add, higher performance vehicle management unit, you can swap that out for a different module and scale that up or scale it down, depending on the end application requirements. And the same thing for the companion computer. You can go with lower performance for lower end applications where you don't need as much compute capabilities, and you can scale that up in terms of compute capability for more complex environments and more complex tasks. Today, we have a range of different solutions available on the latest processors, and in terms of the capabilities of the companion computer and so on, we'll get into that in a little bit more detail. But the main point I wanted to get across on this slide is that you need some kind of a communication and connectivity infrastructure. Here we have two different examples. One is we have a dual CAN bus, and this allows us to have some redundancy. If you want to connect the actual modules to both of these CAN buses, if one of those was to fail, you could immediately switch over to the other one and still continue operation. We also have a TSN Ethernet switch. Today, we're just using it as a standard Ethernet switch, but if you needed real-time synchronization capabilities over Ethernet for deterministic, information from these sensors, you could implement that with just a software upgrade. But the Ethernet is there to bring in some of the higher performance sensors like cameras, radar, LiDAR. They may have much higher bandwidth data that needs to be transported to the companion computer for processing. In the future, that might go down if you do more edge processing in those sensors before sending it to the companion computer. But today, there's a fairly high amount of bandwidth that goes across that network. You also have here modules for motor control, for battery management, and then you also have ultra wideband. This could be used for locationing. I don't think this is widely used today, but this can give you fairly precise locationing capabilities. So this is another area that we're investigating for use for mobile robotics. So let's talk about the how we implement some of this connectivity. So we have the mobile robotics or MRCAN Hub K344. This is a module that's based on our S32 K344 automotive microcontroller. And this architecture basically allows us to provide this internal CAN connectivity. This device also runs, other interfaces in terms of Ethernet. If you want to bring in some sensors directly connected to this module, you could also do that for smaller, lower-end robotics applications. And also, this device could implement, motor control functions and also have safety capabilities that we'll cover briefly in a later slide as well. Okay, so let's look at a little bit deeper at the CAN Hub module and its capabilities. So this design, as I mentioned before, is based on the S32K344. There's also a safety PMIC on there. So if you do need to implement some safety functions or lockstep capabilities here, you can use the combination of the S32K as well as the safe PMIC to have a safe system from a power management perspective as well. The S32K supports 6 CAN interfaces as well as Ethernet, so you can have a T100 base T1 interface. It can support GPIO and other interfaces, This system has a set of standard connectors on there. These connectors are basically using the drone code standard, and this allows you to have a standardized way to connect other modules to this using a standardized connector and cabling a mechanism. And also, as I mentioned before, the S32K can implement motor control functions as well. It has the PWM timers on board and can do BLDC motor control functions if that's desired by almost the same design, basically. So here we're showing the whole S32K kind of range of different processors, the family of devices that are available. You can see we have different number of cores, different amounts of both flash memory as well as SRAM on board. And all of these devices can also support kind of firmware over-the-air update or switching capability with zero downtime. It's got enough memory on there to switch between the two after you update the software. It's got on-chip kind of A to D, D to A converters for connection to analog interfaces. And also it has low power mode, so it can run in standby mode as well as fast wake-up capabilities. And as I mentioned before, this has full ISO 26262 ASIL-D safety capabilities, and we have all the safety collateral available to support that as well. The other connectivity that I was showing on here is basically the TSN Ethernet switch, and here we're using our automotive TSN Ethernet switch capabilities. This is a switch that can support many different ports. In this example, we're just using 4 ports, and we're using a 100 base T1 with 2-wire Ethernet PHYs, and basically to provide just the standard 2-wire connectivity. The idea of using 2-wire interfaces is that in a mobile robot, you don't really have long distances to traverse, and you want to try and keep the weight of the robot down to extend the battery life. So this allows you to basically, have savings on cabling in terms of the weight, and length of cables that you need to run is fairly short. So this is the 8-port Ethernet switch. As I mentioned, we're only making use of 4 of the ports in this design right now, but all 8 ports are available if you want to connect more sensors. 6 of these have 2-wire Ethernet interfaces available. We have 1 that we've wired up to a standard RJ45, and then we have 1 that we wired up for a gigabit Ethernet connector as well, in case a higher bandwidth interface might be needed. And this uses our standard, 10-port Ethernet switch, the SJ1110. We're also using the automotive PMIC, and we have a secure element on here, again, if you need additional security capabilities. And this is in a fairly small form factor, only 75 by 50 millimeter board. And you can get more information on the NXP website related to this design. In terms of the vehicle management unit, so we've actually used our crossover family for the vehicle management unit. This uses our RT1176 family, and this basically provides all the internal vehicle function control. So basically managing the acceleration, the speed, the direction of the actual robot, and it has a direct Ethernet interface to the companion computer. It's also connected to the CAN bus, so it can get data from any of the different modules, including sensors, motor control, battery management, etc., and be able to use that information to carry out the functions, how fast it needs to go, when it needs to accelerate or slow down or stop, and the direction it needs to go in. In terms of the capabilities of the actual vehicle management unit, so we're actually, as I mentioned, are using an RT1176. This basically has 2 cores on there, a Cortex M7 that's running at 1 gigahertz, and you also have a secondary core that's a Cortex M4 that's running at 400 megahertz. I don't believe we're using both cores at this time. We're just using the M7, but if you wanted to perform more functions or need more capabilities, you can make use of that additional core. And also this is a module that can again support CAN as well as Ethernet and TSN capabilities. And also there's a complete reference design available, and we also have all of the information available on the NXP website. And just like the other module, we also gave the option for a secure element. All of these devices, like the S32K, the RT1176, have integrated security hardware acceleration. But if you want kind of, even more robust security capabilities, the secure element as an add-on module allows you to enhance that security capability and also adds a level of authentication. So for example, if you have a faulty VMU and you want to replace this with another board, you could use the secure element and the NFC to authenticate that that is actually a genuine module that you're actually integrating into the system, using security keys to authenticate that, versus somebody, maybe installing a defective or a clone that might affect the operation of the actual vehicle itself. So as mentioned on that slide, the actual vehicle management unit and the RT1176 uses Zephyr as the operating system. This is a very popular operating system, gives you a lot of portability in terms of the application that are running on top. So you could easily switch from like an RT1176, for example, to an S32K or one of our Kinetis or LPC devices, and you can abstract kind of a lot of the lower level hardware capabilities, and it gives you portability from an applications perspective. Also, it's a very small footprint, so it can be used in resource constrained systems like microcontrollers, and is also very ideal for kind of secure connected devices. It's very popular in both IoT and kind of consumer as well as industrial applications. The licensing is also very attractive. This actually has permissive, licenses using Apache 2, which pretty much gives you the license to use and integrate and ship the product in any product with very little restriction in terms of licensing capabilities. We also have CogniPilot implemented on the vehicle management unit, and this is the one that's actually doing all the vehicle management. So this is really like an application that's running on top of Zephyr. And also it's very well integrated with ROS, the robot operating system. So it can work very easily with the rest of the modules in the system, as well as the companion computer. So now let's take a look at, the actual companion computer itself, the NavQ Plus module. This companion computer is actually leveraging our ADRMX A10 Plus. This is kind of our flagship ADRMX 8 product. It has 4 A53 cores, so fairly high performance compute capabilities. It also has a hardware neural accelerator on there for AI machine learning capability. It also has vision processing pipeline, so it can do all the image processing, segmentation, etc. It can support dual cameras, USB, CAN, and also Ethernet interfaces as well. So this would basically be responsible for running kind of the autonomy algorithms and doing the sensor fusion functions, and then basically, working out the actual path and providing that data to the vehicle management unit, which will basically use that to actually control the vehicle and perform the actual mission. In terms of the details on the NavQ Plus, so as I mentioned, this is based on our ADRMX A10 Plus, and our EVK platform, which is our development platform for this processor, actually has a modular architecture itself as well. It has a system on module, which is the processor, memory, and some of the interfaces, and then it has a carrier board which implements and brings out all the I/O. And we use that same SOM module, but we have a custom carrier board here that implements all the different interfaces and connectivity that's needed for a mobile robot. And then also we're using the internal hardware accelerator for machine learning. We have tools and development environment available for that machine learning if you want to customize and develop machine learning solutions. We also use, from an operating system perspective, both Yocto Linux as well as Ubuntu proof of concept. And this is more of a kind of like a desktop release of Linux, if you like, and more friendly and easier to use. And this is also enabled with the robot operating system. And although it's called an operating system, this is really middleware, and allows you to have all the kind of libraries and functions that you need to implement a robot application. The module also has wireless connectivity. So we have Wi-Fi, Bluetooth. As I mentioned, this has the MIPI CSI connections on there to bring in camera interfaces, and the actual module ships with a camera as well as Wi-Fi. There's two Ethernet ports on there. We'll bring out both those Ethernet ports. We use the USB-C on here to power the module. So if you want to actually use it standalone, or you want to actually bring in separate power connectors, you have both those options available in this design. And also, just like the previous modules, we also have optionally the secure element and the NFC available here to authenticate the module and for additional security capabilities. And although the processor has a real-time clock on there integrated already, we did also put the option of an external real-time clock, which is a much more enhanced real-time clock that has additional time stamping and tamper detection capabilities as well. And also for expansion, you have a PCIe slot available as well, so you can add in other functions like 4G, 5G, cellular connectivity, etc. through those interfaces as well. And although we're not using a display in the mobile robot reference design that we have, there may be some examples where you do need a display, like a hospitality type environment. So there is an option to support that as well. In terms of the robot operating system, so as I mentioned before, this is what we implement to support all the different mobile robot functions within our platform. And this is basically providing you with a set of libraries and tools to build a robot application. This includes drivers, advanced algorithms, and also kind of developer tools as well. And at the heart of ROS or ROS2 is really this concept of a ROS graph. And the ROS graph basically describes the network nodes and how they're connected. And these connections between the different nodes then basically define how they communicate with each other. So a node, can basically, publish the services that basically it provides. Other nodes can basically subscribe to those services. And they will basically get the information that's generated, and they can then use that information in any way that way wish. And this is how this modular architecture basically works, that the different modules supporting ROS can provide all this different information, and then the companion computer and the vehicle management unit makes sense and use of that data to actually control the vehicle. In terms of this middleware and the software, this is basically using standardized messages. It's standardized publish subscribe system, and it's implemented in Python, C++, Rust, and other OSs. It's very flexible in terms of the development environment. So we talked about some of the modules, in particular the vehicle management unit and companion computer. And I wanted to briefly explain how we partition the different autonomy tasks between these two different modules. So today what we have is an architecture where most of the functions are actually performed, the compute-intensive functions are performed on the companion computer. This is on the RMX A10 Plus, the NavQ Plus module. So you can see this is more, if the colors are coming out correctly, kind of the orange, bubbles that you see here. So in terms of using the sensors, to perceive the environment, its location, then it basically determines, within that environment, where is it located. It has a set of maps that is created before that it uses to, figure out its location. Then it predicts the path it needs to take in terms of the destination that it needs to get to. That path planning takes place, and then that path is basically communicated to the vehicle management controller, or the vehicle management unit, and then that basically carries out that task in a safe way. And in parallel with this, the actual companion computer is basically using the sensors to make sure that there's no objects in the way, and that it needs to avoid or steer around, and it will basically provide that feedback back to the vehicle control unit to be able to adjust around those. So today, some of that path planning is done in the vehicle control, and some of it is done in the companion computer. And now we're looking at moving, the remaining functions that were in the vehicle management unit over into the companion computer. So we have a complete separation of all the autonomy features versus the real-time control of the actual vehicle itself. So we talked about all the different modules and the capabilities they provide, but at the heart of a mobile robot, you need to have sensors to be able to sense and perceive your environment. And there's a whole range of different sensors that you can use. For vision, you have, cameras, you can use a standard camera, time of flight camera. You can have, RGB or RGB IR cameras for, different environments. You have stereo cameras for depth perception. Time of flight is similar. They give you kind of depth and distance, to the object as well. And you can also have radar. We have our 4D imaging radar that's available for the automotive market. And, that could potentially be used in the mobile robotics market as well, for navigation as well as for safety applications. You also have UWB for real-time locationing. You can also use LiDAR, both 2D, 3D, both for safety as well as, again, for navigation and mapping applications as well. And I'm going to skip this slide. This is just basically giving you that same information, but it's giving you another picture of the actual camera as well as another view of the actual radar sensor itself. Okay. So finally, let's also cover some of the other modules. Again, I skipped some of the other ones because of time, but battery management is also a key part of a robot because that determines how long a robot can operate before it needs to be recharged. And NXP, from our history and the market share that we have in automotive, we have a very strong and a very leading edge battery management solutions available. And we have implemented a reference design that can also be used in mobile robotics. So this is a combination of kind of battery cell controller ICs as well as MCU to provide some of the high-level battery management features and capabilities. So there's a complete reference design, and this is described here on the next slide. So we're using basically, our cell controllers, the actual MC33772. There's also another one available that has support for more battery cells. It's the 33771, sorry, with 14 cells. You can use the automotive MCU or any of the other MCUs depending on the requirements if you need safety or not. So to provide some of the high-level management and also network interfaces to the rest of the actual mobile robot and platform. And again, we have a secure element as well as an NFC to authenticate the battery modules themselves as well, to make sure that these are all authenticated, validated battery modules. Also, you can store a lot of information using the microcontroller in terms of the health of the battery, how it was used. If it was damaged or misused in any way, you can mark that so that you can make sure that it's not used again. So those kind of functions can be performed by the MCU, and you can use the secure element for some of those functions as well. And on this module, we're using NUTX as an operating system. And then we have a whole set of libraries for battery management and the actual application itself as well. So in summary, in terms of NXP, we have a long history in automotive, aerospace, and industrial markets. We have a strong history in radar, RF, security, safety, motor control applications, all of which are kind of the requirements for a lot of the robotics and mobile robotics platforms. We have a scalable range of solutions to match different application needs in terms of microcontrollers and processors. So if you're ready to do a design for a mobile robot or a rover or even a drone, we have the technology and reference designs to help you to accelerate your time to market. And you can go to this NXP website, www.nxp.com/UAV, and you'll be able to get a lot of the information on these reference designs, as well as additional information related to mobile robotics, as well as drone type applications. Thank you for your time.
All right, thanks, Altaf, for that interesting presentation. We already have several good questions, but I want to let our audience know that there's still time to submit more. Use that chat box on the right side. Altaf, are you ready to answer some of these questions?
Yeah, sure.
All right, the first one is a question asking about whether the T1 Ethernet switch is a managed switch.
Yeah, it's actually is a managed switch since it needs to run the TSN protocol as well. So it is fully managed in terms of being able to support like spanning tree algorithms and avoid loops and so on. So yes, it is a managed switch. It can be operated as an unmanaged switch as well, but it does have that capability.
Excellent. All right, our next question is asking, it's referring specifically to slide 7. It says, what is the purpose of the aux IMU and how does it work in combination with the primary IMU?
Yeah, so this is basically for some other applications as well. So, for example, if you wanted to use this as a drone type application where you need, additional axes in terms of altitude and so on, you could have multiple IMUs for different applications that could be installed there. So a vehicle could be operating on the ground as well as in the air. So you may need, additional IMUs to be able to support that kind of use case.
That to me, that just brings up the interesting point, this kind of convergence of autonomous mobile robots, automobiles that are controlled, drones. There's a lot of overlap, isn't there?
Yes, there is, and we actually reuse basically the same architecture for our mobile robot as well as for our drone. NXP runs, some of like the drone competitions. We have like a hover games competition that we run, and that uses exactly the same architecture. There might be some differences in the sensors that you use, but otherwise it's mostly the same hardware, and there might be some small differences in the software that you use as well. For example, you don't need a SLAM algorithm in terms of autonomous navigation that you do on the ground. You typically have additional software ecosystem for drones when they're flying versus when you're driving a vehicle.
Right. Interesting. Next question, a little bit difficulty parsing it, but maybe you can understand it, is they're looking at what one system includes both the microcontroller baseboard and a microprocessor baseboard, and which one is holding the master role and can reboot the other when necessary.
So they're really operating kind of independently. There's a communication interface between them in terms of sending sensor data, navigation, algorithm analysis results to the vehicle management unit, but they're really booting and operating completely independently. The reason we did that is really to be able to scale these two functions separately. If you looked at the RMX A10 Plus and the actual navigation computer that we're using here, it actually has a Cortex M core integrated on chip as well. So if you wanted a more cost-effective solution and you wanted a lower cost solution, you could actually move those vehicle management functions onto a single device like the RMX A10 Plus. And then that question is more applicable in terms of which core would boot first and which functions would operate first, the Cortex A cores or the Cortex M core. Most likely you would be bringing up the Cortex M core first to make sure that the vehicle is in a steady state and not moving as you actually calculate where you are and determine the route that you need to take. But you have the option to choose either way. You can boot the Cortex A first or the Cortex M7 if you have a more integrated solution.
Okay, that's helpful to me at least, and hopefully to our questioner. Next question is, are there any ready solutions to control several robots simultaneously, coordinating them like in the swarm kind of applications?
There are some open source, initiatives that are going on that allow robots to collaborate. That could be operating as a swarm as well, but also for other use cases. For example, if you're in a hospital or an airport, etc., typically you see these days, there's autonomous sweepers that are cleaning the corridor and so on. And you may also have a delivery robot that's actually in the same space, maybe the same corridor, that needs to deliver something. And they need to be able to communicate with each other so that one can give way to the other. As humans, we don't really think about that. We just kind of walk past each other. But if they were operating independently, there's a high probability that they might run into each other. So they have to be able to communicate with each other and give precedence to one over the other. And that might also be based on the actual situation as well. So, for example, in the scenario that I talked about in a hospital in a corridor, if there's some kind of a spill in the corridor and the sweeper is actually cleaning that up, you probably want to give that priority versus a delivery zone and have it stop. Versus if it's the other way around, there's no spill or so on, you might have the sweeper stop and let the other robot through. So there's various different open source projects that are investigating that and driving that activity. And there is activity going on kind of like swarm type activity as well. In an industrial environment like a warehouse, we haven't seen many applications that actually have a need for that. Typically, these robots are not communicating with each other. They're communicating with the actual control center itself, and it's basically determining the paths that they need to take. And it ensures that they don't really run into each other based on the instructions that it's giving these robots right now. But there could be potential use cases in the future where two robots could combine to carry out a more difficult task or lift a heavier load or something. So definitely see applications for that in the future.
Okay, excellent. Next question is, does NXP sell a mobile robot as a complete system or only the individual modules?
So we do have a complete system. We primarily are using it for some educational activities right now. We have like an NXP Cup competition where we basically give away these units to students, and it allows them to basically use a small kind of cost-effective vehicle to practice and actually implement, autonomous vehicle or autonomous, software capabilities on a platform. And we run a competition that uses that platform. We do want to be able to offer that to the general market as well, but we just need to complete some of the additional certifications that are needed to be able to offer that for sale. And we expect to do that later this year, so watch out for that. But right now, all the modules are available. And we have shown the actual platform at various different TADE events, etc. And we'll be showing it at Embedded World in early April as well, the actual robotic platform. And that's the one that we'll bring to market later this year as we complete some of these certification processes.
All right, well, stay tuned for that then. Our next question is, do the NXP reference designs come pre-installed with all the software for mobile robotics?
Yeah, so there's some amount of software that's already pre-installed. In other cases, we provide links in the documentation to images on the NXP website where you can download an image onto an MMC card, for example, and plug it into the board and make it operational. That's typically the operating systems that come in that form. And then for the actual application software, itself, for example, the ROS2, middleware that we talked about on the navigation computer, the NavQ+. We provide a link to the open source community because we're using just the standard package. There's no additional, information that is needed. That just needs to be built with the operating system that we're providing to download and run onto the board. And all the instructions are provided in the quick start guides that we provide on our website. And they also provide the links directly to these communities, as well as any additional documentation that might be needed to get the module, operational.
Okay. Question here is, can the LiDAR sensors be replaced by radar?
So that's a good question. Typically, 3D LiDAR is a lot more accurate in terms of precision, in terms of measuring distances than traditionally radar has been. But now with advances in radar technology, for example, NXP has 4D imaging radar now, and also with new kind of RF and antenna technologies, it's possible to get very close to similar accuracy as LiDAR. So there is a possibility that in the future, radar could potentially, replace LiDAR in some of the use cases. In mobile robotics, today, from a safety perspective, 2D LiDAR devices are what's used primarily for safety to detect distances and how far away the robot is from a particular object. And those need to be safety certified, those modules. So, radar module, are just starting to, I think, go through some of these certification processes so they could replace some of these functions and also meet the same accuracy needs. But I think it's still more work to do in that front in terms of solutions being available. But yes, that is a possibility, and that should reduce the cost of these sensors, because radar tends to be a lot lower cost than some of the LiDAR solutions that are available.
Okay. This question is asking us, what strategy does NXP recommend to ensure a 10-year production lifetime?
So you mean for the end system, in terms of, is the qualification process for the devices, also ensuring from a supply chain perspective that, you have everything in place to be able to secure manufacturing and manufacturing capacity for that period of time as well. Most of our devices, if not all of the microcontrollers, all of the processors that we provide, we typically guarantee those for a minimum, lifetime of 15 years from a supply perspective. And we also, from a quality, reliability, and qualification perspective, typically warranty these for a minimum of 10 years from an operating life perspective as well. So the components themselves are capable of doing that. From a system perspective, obviously, you need to take into account a lot of the other components as well, like motors, drives, some of the other, sensors and so on that you're using. But overall, we have many applications, industrial, aerospace, that typically have systems shipping for not just, 10 years, but 15, 20, 25 years. And we still continue to ship some of those products in those applications.
Yeah, and that's really a good thing for people to think about when they're looking at systems, if they're coming from the more consumer electronics world and moving into robotics. Those are questions they really need to be asking when they're looking for the component, is how long are they going to be able to get those?
Yes, exactly. And also, from a quality perspective, what's the mission profile for those, right? So if you look at consumer versus automotive versus industrial, the actual mission profiles, or if you like, the operating environment and expectations are very different. Consumer products, you don't typically ship a consumer product for 10 or 15 years, right? So
Right.
you're redesigning those on a fairly fast, redesign cycle. Automotive, you don't drive your vehicle 24 hours a day, whereas a factory needs to operate 24 hours a day. So it's different mission profiles and different qualification tiers. And we support most of our devices for all of those different tiers, so people can get the right solution for the application that they have.
Very good. All right, next question here is, are there any wireless mesh network modules available?
So in terms of wireless capabilities, there's obviously, a lot of different wireless technologies that you can use. We have used, for example, Thread, from NXP, originally that is kind of implementing a mesh type network as well. You can also do a mesh overlay or a Wi-Fi network. So this is basically additional software that you can use to create those mesh networks. As I say, in a mobile robot context, we talked about the use case earlier for swarms and so on. If that, materializes, then you will definitely need this low latency mesh network. And at that point, maybe 5G or that kind of a network might be more suitable based on its reliability and low latency versus a Wi-Fi network, because you're going to make these decisions and communicate in almost real time between these robots to make those decisions. But yeah, mesh networking for wireless has been around for quite some time, and you can pretty much implement a mesh network over most wireless networks.
Okay. Next question is a fun one here. It says, you mentioned that the student teams can obtain robotics sets for free for competitions. Can you please provide more details?
Yeah, there is actually, if you go to the NXP website and just type in the search window NXP Cup, it will take you to a website, and there is actually a link there to actually apply to take part in that competition. So if you want to go ahead and fill out that application, then our team that actually works on that competition will assess the actual use case and determine who they support from a supply of the mobile robot platform perspective.
Okay, so we'll check out the NXP Cup. This question, the one that came to my mind was, you were talking about the incredible AI ML performance, 2.6 teraflops or whatever it was on the neural thing. And it's like, For developers who keep hearing about AI, ML, and really want to start adding it to their robotic applications, but maybe they haven't done it yet, do you have any general advice on what are some of the easiest ways to get started in using AI, ML in these applications?
Yeah, really, I think the easiest way is to actually start with something like the NavQ Plus module that we have. There's a lot of different use cases that you can actually implement on that. And a lot of those are actually built into our standard Linux SDK that we provide. In many cases, what we do now is we don't just provide like a Yocto Linux distribution that runs on the board, but there's canned, demos that are available that you can basically run, immediately as soon as you boot the board. So those will be implementing things like, facial recognition or object detection, recognizing what that object is, and so on. So you can try those canned demos first of all, and you can look at all the source code as part of the SDK, and then really try to, modify that. So maybe if it's doing object detection, it's detecting maybe, I don't know, different types of, fruit or something, orange, banana, pear, or whatever. Try to add another object there in terms of additional learning capabilities to recognize something as another object, and then maybe build your knowledge up from there to start building a new model and actually generating a new model. Once you become more of an expert, you can take raw data and curate that data using our development tools as well. So build a completely custom AI machine learning solution. But I would start with the basic demos that come with the SDK, play with those and try to kind of modify those and bring up your learning and expertise that way.
Yeah, it seems an easier hill to climb than just starting blind.
Yeah.
Looks like we've answered all the questions so far. Well, wait a minute just to see if anything else comes in. Altaf, is there anything you'd like to elaborate on as you look back on the Q&A here, or make sure the audience takes away from your session?
Yeah, there is a lot of work going on in mobile, robotics in terms of innovation and so on. But a lot of the innovation is now happening around sensors. I think on the compute side, it's fairly well defined now, and in terms of autonomy, adding the calculations that you need and acceleration that you need for SLAM. So processors are starting to add even hardware acceleration for those mathematical functions in the form of either DSPs or other technologies to accelerate those SLAM algorithms. But I think more of the processing is going to move to the edge. I think you're going to be able to use smarter cameras, smarter other sensors in terms of, radar modules. I do see UWB potentially being adopted, down the road, as well as the more precise locationing technology. And that would basically, allow the central compute to know exactly where it is at any given time without having to calculate that. So again, reducing the overall performance requirements for the central computer and having more of a distributed approach. That allows the robot to scale with different number of sensors, with different compute platform to address a wide range of different applications. So you can have one kind of architecture that could address a warehouse robot or a hospitality robot or a delivery robot, and basically just scale up and down the actual compute and the number of sensors that you need for those different applications. So those are kind of some of the areas that we're investigating, and we're also looking at fusion of different sensors like radar, vision together to see if they can provide more efficient, mapping and also navigation capabilities than, those, sensors being, separate or as an alternative to potentially using, LiDAR technology.
Excellent. Well, it looks like we've covered all of our audience questions. So thank you again, Altaf, for your presentation and a great discussion during the Q&A.
You're welcome. Thank you for your time.
Before we wrap up, I'd like to announce our giveaway winners for this session. 2 winners will receive an event t-shirt and a 6-in-1 multi-use screwdriver, courtesy of Mauser Electronics. Congratulations, Chris Konowski and Mark Blondin. We'll contact you after the event to ensure we have the information we need to send you your giveaway package. And folks, please be sure to check out the other live sessions happening today. In just a moment, you'll be redirected to NXP Semiconductor's booth page, where you can browse and access their other content. Thank you for attending Control Automation Day 2024. I encourage you to check out today's other upcoming keynotes, live sessions, and published content.